Alright, in today's lecture we'll be going over Kepler's 3 laws of gravitation. So the first law is the law of orbit. You might think that the planet goes around in a spherical orbit, but it doesn't. In fact, it goes around in an elliptical orbit. Basically, properties of ellipse. They have two foci, one is at F and the other we'll call at F prime. And the line going through the longer end of the ellipse is the semi-major axis, and the axis going through the shorter end is the semi-minor axis. And according to the law, at one foci lies the sun. So basically, what is happening is that your planet is orbiting around the sun in an elliptical orbit, and the sun lies at one foci. So another property of an ellipse is its eccentricity. Basically, that's how much like an ellipse your orbit is. So having an eccentricity of 0 is a circular orbit, and anything other than 0 means it has an elliptical orbit. And most planets have an elliptical orbit, even though not as extreme. The second law is the law of areas. Basically, what this law states that the area that the planet travels between 2 points and the foci, if they're the same as another group of areas, that means the time elapsed is the same. So right now I'm drawing two locations of the planets, and the area that's like the pizza shape is basically the area between the positions and the foci. So I'm going to draw this between one with a greater radius and one with a smaller radius. As you can see, we'll assume that the areas of these shapes are the same. What does this mean? That means the time it took from the planet to move from those two positions are equal in time, even though they may not look at it like it. So for the one that has a smaller radius, it looks like the surface, the arc is greater. What that means is that it's traveled more distance, so it's faster when it's closer. But the elapsed time is the same, even though it's faster at smaller radius. Let's try to develop some intuition on this, and we'll do this by looking at the conservation of angular momentum. And basically, what this law states is that the mass times the velocity times the radius is the same at all points of the orbit of basically circular or like elliptical motion. So let's take a look at when the planet has the greater radius, and we'll define the velocity as velocity initial and radius initial. And to reiterate, it's of the planet that's further away, the one that had a greater radius. So let's plug in these numbers these variables into our equation. We get m velocity initial times radius initial equals m, and this velocity that we're trying to find. And for the one closer, let's just say that it's half the radius of the one further away. This will make it a lot simpler to see what I mean. We'll cross out the variables similar to both sides, and we get this 2 velocity initial as this new velocity for the one closer away. What this again proves is that it's twice as fast. The planet that's closer with smaller radius is twice as fast when the radius is twice as small. Alright, so now we're going to look for mathematical proof for why the second law is as it is. Let's look at the planet's distance traveled as a huge chunk in time, which would be the big pizza. But that's not as good as if we looked at it as an infinitesimal change. So we'll determine the point between the planet and the foci as r, and the distance that it travels in between 2 points we'll label as the arc length, which is s equals r theta. For infinitesimal distances, we can treat the area traveled as a triangle, so we can look at it as half base times height. And if we plug in our values, we get half r squared theta. Kepler's law looks at area in terms of time, so we'll find the derivative of both sides, which gives us half r squared d theta over dt. And this gives us half r squared omega. Omega looks good here because omega is constant due to the conservation of angular momentum. However, we want to prove it even more by setting the angular momentum's term equal to the change in area over change in time. If we do that, what we do is we divide by 2m, and that would equate the angular momentum to the change in area over change in time. And the third of Kepler's laws, number 3, is his law of his gravitation is the law of periods. And basically, what this law states is that the period squared is proportional to the radius cubed. So basically, the greater the radius, the greater the period. And we can prove this by doing force equal using the gravitational equation G_me_m over r squared and set that equal to the centripetal force. We know that the velocity equals omega times r from rotational motion, and we know that omega equals 2 pi times the frequency, and the frequency is the inverse of the period, so 2 pi over period. So we ultimately find that velocity is 2 pi r over the period. And now that we know v, we can plug that into v squared. So what we really get is gm mass of Earth times the mass of the planet over the radius of Earth squared, or the radius of where the planet is, equals 2 pi r over t squared over 1 over r. In this equation, we got rid of the masses of the planet because they don't matter. So the period is independent of the mass of the planet. And if we rearrange both sides to isolate the t, we get t squared equals 4 pi r squared times r cubed over gm. And we can tell that it's t squared is proportional to r cubed because 4 pi r squared over gm, which we isolate,